Let's talk about matrices and determinants now. We need to cover all these 4 topics in our course. First is the important properties of matrices and determinants. And then we will talk about the eigenvalues and vectors, and we will try to figure out the vectors and values simultaneously. And then we'll talk about how to create or form the Echelon form by using the augmented matrices. And also, lastly, we'll do the LU decomposition. And lastly, we'll take some important problems in our course. Now let us see how a matrix is represented. A matrix of size m cross n is represented as a box here with m rows and n columns. In this case, we have m equals to 3 and n equals to 4, means the number of rows are 3 and number of columns are 4. If you see here, A is equal to, means A is a matrix of order 3 cross 4. It means 3 rows and 4 columns here. And also there is a matrix B, which is having the same number of rows and same number of columns. We can add these 2 matrices like this. And we may add B to the A, which is this. It means that if we add A to B or B to A, the answer is same. Thus, it shows commutative property of the matrices. If our B matrix would have been of order 2 cross 4, then the addition was not possible because the order is mismatched in both the matrices. So you can say that matrices of different orders cannot be added. Also, you may evaluate this matrix algebra by doing like this. You can distribute A to B and C. And also you may write B plus C as C plus B as of the commutative property, and you can distribute A over C and B. You can write like this. This matrix algebra represents the multiplication of A with B in the same order. And we take A first and then B in the second position. We take the first row of A and multiply with the first column of B. Then we multiply -1 with 3, 5 with -1, 2 with 0, and add them all. Now keeping the first row as the same position and increment the column number, which is this one. And now do the same operation again. -1 into 2 plus 5 into 5 plus 2 into 3. Add them all. Now again incrementing the column number, do the operation again. You're gonna get this 12. And do it again. And you'll get 29 for the next one. Now in the rows, now you have to increment 1 row here and do the operation for each column here. So you get multiplication of A with B. In the same order you get this matrix. Here the matrix size is 3 cross 3 and here is 3 cross 4. The column of this A matrix is equal to the row of this B matrix, then the multiplication is possible, otherwise not. It means that here 3 is equal for these 2 matrices. That's why the multiplication was possible, otherwise not. And now let's think what would happen if B would have been multiplied to A in the same order like A is multiplied to B. I'm talking about, is AB is equal to BA? I guess no, because if you multiply B to A, it cannot be multiplied, as 3 cross 4 is there in for B and A is having 3 cross 3 and 4 is not equal to 3. This 4 and 3 is mismatching here, so you cannot multiply this matrix. That's why AB is not equal to BA. Now here's a property here. You can multiply B to C first and then A to BC. But here we have multiplied AB first and then AB to C. It means that if these are same, that's why the matrix is showing us the associative property. Let R be a real number now, and if you multiply R to AB, and you can take this R in front of A like this, or you can also take inside in front of B and you can multiply R to B. Let this be a real number here, and if you multiply R to SA, and already S is multiplied to A, by placing S in front of A, you can take R and S as a whole and then can multiply with A, but the order is same. Here is SRS and here is RS. You cannot take a SR. One thing, just remember one thing, in matrix multiplication the order is very much important. You cannot reverse the order. Now let's discuss the transpose operation here. We need to interchange rows with columns here. Let's take the B matrix. Now we interchange the rows with the columns here. Now if you note here, the first row has become the first column here. And the second row became the second column. Third row became the third column. And the order has also changed. It was 3 cross 4 and then now the order is 4 cross 3. We represent the transpose of B like this, B transpose. Let's see the first property of transpose is, if you do the B transpose first, and then again the transpose of the whole, then you get the same B matrix. It is obvious because this transpose is again transposed and convert to this matrix, the original one. The second property says that A plus B whole transpose give you A transpose plus B transpose. And it is also obvious. You add two matrices and you take the transpose here and also take that A matrix transpose and add it to B transpose, you get the same one. You can try with some examples. I will leave it for you. The third property state that AB transpose gives you B transpose and A transpose, and which is the reverse of AB transpose in the opposite order. Now let us check the fourth property here. If A is multiplied with this real number R and is taken as a transpose, and you can take the real number out and A transpose is left out. Okay, you can try out with that example. I'll leave it for you. You may note down these important properties of matrices. Now let's discuss the determinant of a matrix. A determinant of a matrix A is represented as like this. Note that you can find the determinant of a matrix A only if the order is same for both the rows and columns. It means that the matrix should be a square matrix. Why it is square? Because it is having 3 rows and 3 columns, or same number of rows or same number of columns. Now let us figure out the determinant of this matrix A. You may not find out determinant of this matrix B because it is having unequal rows and columns. Before finding out determinant of a matrix A, you need to know one thing, which is cofactors. What are cofactors? A cofactor is given by -1 to the power of m plus n into minor of mn. For example, if I take this element A, the cofactor of A would be, now if you notice here, the row number is 1, the column number is 1. So m is 1, n is 1, place in this formula here, and minor of 1, 1, which is equal to EFHI. Why? Because I have cancelled out the row number and the column number for A. I get EFHI. Similarly for 1, 2, which is B, we can check out the cofactor for B like this. The main problem is how to solve this one. We can do is what? Multiply D with 2I minus F into G. Okay, and this one is -1 because -1 to the power of 3 gives you -1, and you can multiply this -1 to this di minus fg, you get the answer for cofactor for B. Now you know how to find the cofactor. You may use this cofactor to find out the determinant of the matrix A. To find the determinant of the matrix A, I have taken the first column here, and for each element I've taken the cofactor and multiplied with that element. For example, in this case, we have taken -1 into the cofactor of -1 plus 0 into cofactor of 0 plus 3 into cofactor of 3. And if we solve this one, you get the determinant of the matrix. Sometimes we determine matrix is represented as a triangle, which is equal to delta. You could have taken this second row and take each element and with the cofactor along with it, multiply it and add it, you get the same answer, the determinant of A for both of them. Now let's talk about the adjoint of A. Adjoint of A matrix is given by, here every element is the cofactor for the respective element in the position given here. For example, -1 is at the row number 1 and column number 1, and we place the cofactor of -1 in the same row and column, and you get the adjoint matrix for every one of them. This is the adjoint matrix of A. But if you talk about determinant, it will represent it like this. Now let's talk about inverse of a matrix. The inverse of a matrix is represented as, and it is given by, now you know the adjoint of a matrix A, and also you can find the determinant of A, and you can place the values here, and you can find the inverse of the A. Note that this is adjoint matrix, not determinant. It will show you some value like this. The result is a matrix, not a real number. One should note an important property of adjoint of matrix and inverse. If the inverse of A is equal to 0, then the matrix is called non-invertible and singular. Else, it is invertible and non-singular. The reason can be like this. If the determinant is 0, place this 0 here. If you place 0 here, the inverse of the matrix A would become infinity or undefined, so which is not possible. It means that we will not have any other image of this matrix A. So it means that it will have a single image of this matrix. It is having a single image, that's why it is singular. If it is having the inverse, then it is non-singular and invertible. The determinant of a matrix A is a real number like 2, 3, 4, then the inverse of a matrix exists, otherwise not. Let us now check the first property of inverse, which is like this. AB inverse give you B inverse, A inverse in reverse order. It is quite similar to that of transpose, which was like this. AB transpose give you B transpose, A transpose in reverse order. You can keep a memory map like this. Now what's this property here? ABC whole inverse gives you C inverse, B inverse, A inverse in reverse order. Also you can also map with this of transpose. Also note this property, A inverse, again whole inverse gives you A again. It is quite similar to that of transpose or even. Also you may check this property. A transpose whole inverse gives you A inverse whole transpose. You may also check this property and confirm with an example. I will leave this for you. Let's take the first property of determinant here. Let A is a matrix, and if I multiply a real number R to A and take the determinant of RA, then it is equal to R to the power of n into multiplied with the determinant of A. There we have taken an example of this matrix A. Here the order is 3, so here n is equal to 3. So if R is multiplied to A and determinant is taken, it means that for every row or column this R has been multiplied. So for each row or column we take R as common, and cube of R has been taken outside of A. That is why we have R to the power of n in the generalized case. Also you must check this property. A transpose determinant is equal to determinant of A. Okay, transpose or a single matrix doesn't matter, but determinant is same. Also you must check this property. The determinant of adjoint of A is equal to determinant of A to the power of the order minus 1. In this case, the order is 3. Put here 3 minus 1, which is equal to 2. And if you take the adjoint of this matrix and take the determinant, which is equal to this one, the right hand side. Also you may write like this. Adjoint of A, which is equal to the previous result, which was determinant of A to the power of n minus 1, to the whole power of n minus 1. All you need to add this n minus 1 as a power of the term which is left in the previous one. You must note this property here. If you see determinant of A inverse is equal to determinant of A to the power of minus 1, which can be written as, it means that you can take this minus 1 out of the determinant and place outside, or you can simplify as like 1 by determinant of A. One of the most important property of adjoint of matrix A is A into adjoint of A is equal to adjoint of A into A. Here you can see that the commutative property has been satisfied in this case, but we have already done this formula. How? This A to the right side like this determinant of A in the left side like this. Now place a fraction in both the sides, and you can write I by A, which is the identity matrix, divided by the A. We can write it A inverse, and we have already seen the formula for this. Now if we interchange one row with the other row, then you get the determinant sign inverted, which means that, now consider this case, I have inverted the row number 1 with row number 2. In the previous one, the determinant is minus 1, but in this case we have determinant is 1. This sign is inverted. Now consider this case with matrix B. Here row number 1 and row number 2 is identical. Then the value of determinant would be 0. Consider that you want to multiply a real number 3 into a matrix A, and it is having determinant, so A is the determinant. So you multiply this 3 to every element of a row or column. I have multiplied it to row number 1. You could have done like this or this. Let's see the fifth point now. If value of determinant D becomes 0 by substituting x equals to A, then x minus A is a factor of D. You will understand this important point when I will take the problems. For now, just leave it out. Let's see the fourth point. Express sum of other number. Here we can express this determinant A as a sum of the determinant, and this some numbers can be break down into 2. For example, in this case we can break down this matrix into 2 determinant. We have divided this determinant into 2 determinant, where the middle column has been separated out like this. 3 plus 2 gives 5. 1 plus 2 gives 3. 2 can be written as 3 and minus 1. The last important property of determinant is you can find the area of a triangle by putting the coordinates here. For example, in this case we have 3 coordinates having A, B, D, E, F, G. Place here A, B, D, E, F, G, and the last column should be 1. And you can divide the whole determinant by 2. You can get the area of the matrix. Now consider a matrix of order 2 cross 2 having 4 elements, 2, 1, 6, 4. Now let us figure out the eigenvalues and vectors of this matrix A. In order to find the eigenvalues and vectors, you need to know how to write the characteristic equation for this matrix A. The characteristic equation is given by, this equation states that you need to add minus lambda to the diagonal elements of this matrix A, like this. Now you need to add the determinant to characteristic equation and also to this matrix A. Now you need to calculate the determinant. How will you calculate the determinant for 2 cross 2? Multiply the diagonal elements and subtract them. In this case, we will do this and equate this determinant to 0. On solving this equation, you will get this one. On solving with the Sridhar's rule, you get lambda 1 equals to minus root 7 plus 3 and lambda 2 equals to root 7 plus 3. And let's now put this lambda 1 in this place. Okay, if you place here in this whole equation of matrix, you get like this. Now we need to convert this determinant into matrix like this. and add a vector x1 and x2 in front of it, like this, and equate it to 0, like this. You can augment this matrix. Now all you need to do is create one here, okay, in this place, so that you can change the entire row. Now if you see here, I've written an equation here. You need to change the row 1, which is the left side of the arrow, and you need to write the row 1 and divide it with root 7 minus 1. Now the second term, you need to rationalize it by doing like this. You need to take 1 by root 7 minus 1 and multiply with root 7 plus 1 and also divide it by root 7 plus 1. This would give you root 7 plus 1 divided by 6. So you may replace root 7 plus 1 divided by 6 to this place. Now in the second row, you need to create 0 in the place of 6 using the row 1. You can write the equation like this. Now if we write this equation like this, 6 is placed in place of R2 and R1 is 1. So 6 minus 6 times 1, which becomes 0. So 6 is changed to 0. If we talk about the second column, the row 1 and second column is multiplied with 6, which gives me root 7 plus 1. And if we subtract root 7 plus 1 from the row 2 of column 2, it will give you 0 again. Then root 7 plus 1 is also changed to 0. Now you need to multiply the matrix 1 with the matrix 2, which is 2 cross 2 into 2 cross 1. The resultant matrix will become 2 cross 1 itself, like this. Now 0 is replaced with this 0 matrix of 2 cross 1, and this matrix is also of 2 cross 1. You can compare these two matrices and form an equation like this. And you may solve this one by finding the value of x1 equals to minus root 7 plus 1 divided by 6 x2. And for the next row, 0 equals 0, you may write x1 equals to x2. Now take these two 1, form a matrix, and cancel out x2 and x1 from the left side, like this, and place 1 in place of x2. Like this, we have formed a vector for this lambda 1, and you may try out with the same procedure for lambda 2 even. And if you try out for lambda 2 equals to root 7 plus 3, you will get this kind of vector, this one. And you could have named this x1 and x2 with v1 and v2 for vector 1 and vector 2, like this. Let's talk about the trace of a determinant. The trace is the sum of the diagonal elements of a matrix A. It is represented as dr of A, like this, and it is equal to 2 plus minus 2 plus minus 1, which gives me minus 1. Let us now figure out the eigenvalues for this matrix, the determinant of A. The procedure is same. We need to create the characteristic equation by which we have to place minus lambda in front of the diagonal elements first. Now if you find the determinant by doing the same procedure, the method will be very much tedious. So I'm giving you a quick tip to solve such kind of problem. Just follow me. So the trace of the matrix A is given as minus 1, okay, because the diagonal element sum is minus 1. What about the minor? For calculating the minor, take the first diagonal element, which is 2, and cancel the row and column for 2, and take the minor, which is minus 2 and 1, 3 and minus 1, and cross multiply each one of them and place negative sign in between to get. Similarly, you take minus 2, and what is the minor of minus 2? Cancel the row number 2 and column number 2, and you get this element 2 into minus 1 minus 4 into 0 gives you minus 2. Place here minus 2. Also take the third diagonal element, which is minus 1, take the minor. 2 into minus 2, which gives you 4. 4 minus 1 into 0, which gives you 0. And so it is minus 4. Place here minus 4. We get minus 7 in total for minor. And what about the determinant? determinant is -2. Place the values in this equation. You get. Now you may solve this equation, cubic equation, by any other method, by hit and trial, and then divide the factor to the remaining portion of the polynomial and find out the value of lambda. And you may find out the lambda value like this. These three lambda values are the eigenvalues for this determinant A. Also, you may use this equation for 2 cross 2 matrix determinant. You can place the trace here, determinant here, and find out the value of lambda. It will be the eigenvalues. Now let's talk about the Echelon form now. This form is very important for solving simultaneous equations of 3 variables and 3 equations. And in this case, let's just find out the Echelon form for this determinant. There's an algorithm to it. Firstly, the algorithm states that in the last two rows for this 3 cross 3, make the here place here 0 and place here 0. And how it will be created is, you can follow the equation like this. If you notice here, the equation is written in such a way that R3 is 4 and R1 is 2. If you notice here, R3 is 4 and R1 is 2. And if you place 4 in this place and R1 as 2, 2 cancels out, and 4 minus 4 will become 0. It will replace this 4 with 0. In the same way, R2 is 1, R1 is 2. If you place R2 as 1 here, R1 is 2, 2 cancels out, and 1 minus 1 becomes 0. So this means that we have to do this operation for entire row, R3 and R2. Let us do it. And in the next step of the algorithm, try to bring 0 in this place of 3. How can you make it 0? With the help of row 2, not with the help of R1. See, in the first case, in the first step, we have made this place and this place 0 with the help of R1. But in this step 2, we are making the row 3 as 0 with the help of R2, not with the help of R1. So let us write an equation which could bring it happen. If we note carefully about this equation, R3 is placed here in front of the minus sign, and R2 is minus 2, which is placed just below it. And if you place R3 as 3 minus 3 by minus 2 into R2, which is minus 2. Minus 2 minus 2 is cancelled, and 3 minus 3 becomes 0. So now let's figure out what is the change happened in the row 3. So we have got the Echelon form for matrix determinant A. And most important thing, a property has been identified by the researchers that if we multiply the diagonal elements in this Echelon form, we get the determinant of the matrix A. Let us calculate. Note one important property of eigenvalues. The sum of eigenvalues is equal to the trace of the determinant A. Okay, if you add all the diagonal elements, and then it should be always equal to the sum of the eigenvalues. In this case, there are 3 eigenvalues, and if you add them all, you get the trace of the matrix determinant A. And let's say, and the property is product of the eigenvalues is equal to the determinant of A. In this case, the determinant was minus 2, and we got the minus 2 as determinant of the eigenvalues if we do the product. But note that one thing. The diagonal elements were 2 minus 2 and half, but it is not equal to the eigenvalues. Okay, maybe the product of the eigenvalues is equal to determinant of the matrix A, but also the product of diagonal elements is equal to the determinant of A. But it is not necessary that the diagonal elements in the Echelon form is equal to the eigenvalues of the A determinant. Let's discuss how to solve for x, y, and z using the 3 simultaneous equations, and each having 3 variables x, y, and z. We'll use the Echelon form to solve such problems. You need to write all the coefficients of xyz in this way: 2, 1, 4, 1, 2, 3, 1, 1, 1, because they are the coefficient of the xyz, and the right side of the equal to should be written here in the right side of the line, like this: 7 minus 1 and 2. And start applying the algorithm for converting this matrix into Echelon form. Now let's start converting this matrix into Echelon form, as I told you the procedure above. As stated earlier, we need to create 0 in this place and in this place. I'm using two equations to do this. And now, after applying these equations on this matrix, I got this matrix. I created 0 in this place and in this place. Instead, we have also 1, 0 to be formed in this place. And this can be done by this equation. Now we have created the Echelon form like this. Now we need to create the normal matrix form by using this Echelon form like this. I have added 2 cross 1 column matrix in between the augmented matrix and the normal matrix. Now you can multiply this 2 cross 2 matrix with 2 cross 1 matrix and get the following equation like this. Now you may solve the value of z and put here, and you can solve the value of y and again put here. You got the value of z and y, you can get the value of x. It means that you have solved the value of x, y and z using the three simultaneous equations and 3 unknowns. This was an application of the Echelon form. The name of this method is Gaussian elimination. It is the best method to solve such problems that I prefer. Now let's discuss LU decomposition. In this method, we want to decompose the matrix A into 2 other matrices. The other 2 matrices are the lower triangular matrix and upper triangular matrix. That's why the name comes like this, LU decomposition. Now let us take the previous example. The values are the same, but we have just removed the augmented portion of this matrix. Now we have used these 2 following equations to bring 0 in this place and also 0 in this place by this equation. And this is our Echelon form for this 3 cross 3 order matrix. This matrix is called the upper triangular matrix, and we need to create the lower triangular matrix by doing like this. And this blank spaces, this rectangular box, should be filled with the half, half and 1 by 3. Let me show you how. As we have created 0 in this place by using this equation, R3 gives R3 minus half R1. That's why this factor is the main factor which is used to have that decomposition. So I'm using this half, and note that we have a minus sign here, so do not take that minus sign, only take this half and place in this box. Similarly, we have made 0 in this place by using this equation, and we have used this factor half to do this. So let me place this half in this box. And lastly, we have made 0 in this place by using this factor 1 by 3. Neglect this minus sign and place 1 by 3 here. So till now we have decomposed A into 2 matrices, L and U, having 6 plus 3 non-trivial elements in both the matrices. Let's start from the beginning. We were solving these 3 simultaneous equations having 3 unknowns. We converted it into matrices. Now we have decomposed this A matrix into 2 other matrices, L and U. We kept the other remains same. And now we will take these 2 matrices. The order of the first matrix is 3 cross 3 and the order of the second one is 3 cross 1. That's why the resultant would be 3 cross 1. We will replace these 2 matrices with 3 cross 1 matrices having Z1, Z2 and Z3 like this. Now we can write the following equations like this. After solving these 3 equations, we have got the value of Z1 7, Z2 equals to minus 9 by 2, Z3 equals 0. Now we will take these 3 values and place in this equation. But can you solve for x, y, z? Yes, you can, because we have done already. You will get x equals to 5, y equals to minus 3, and z equals to 0. The application of the LU decomposition is to find out the value of unknowns in the three simultaneous equations. Let's talk about the rank of a matrix now. Let's now figure out the rank of the A matrix. The rank is the number of non-zero rows in A. The number of non-zero rows in A is 1, 2, and 3. It means the rank of the matrix A is 3. If we talk about the augmented portion, then we have to take the whole matrix. And if I take the whole matrix also, then even we will have the 3 rank, because there are 3 number of non-zero rows. What about this? The rank of the matrix A is 1, 2, because there are 2 number of non-zero rows. This row is 0. We will have the rank equals to 2. If you talk about the whole matrix along with the augmented portion, we will have 3 rank, because the number of non-zero rows is 1, 2, and 3. Rank is 3. Now you know the rank of a matrix. Now you can figure out which of the following equations can be solved or cannot be solved. Now let's figure out which case is applied on each of the matrices. Now let's take the first one. The rank of A is equal to 3. Rank of B is also 3. The case is rank of A is equal to the rank of B. And if the rank is 3 and number of variables n is equal to the number of non-zero rows, which is the rank, then it is a unique solution. The system will give you a unique solution. And if the number of variables increases and the rank remains less than the number of variables, then infinite solutions may be possible. So in this case, we have unique solution. Let's take the second one. The rank is 2 in this case of A, but in this case of B it is 3. If the rank is not equal, then there is no solution. Let's take the next one. Here the rank is 2 for A. For B it is also 2. Then we can have the solution infinite or unique. And now if we say that number of variables is equal to 3 and the rank is 2, then it is an infinite solution. This means that the system will have infinite solutions. What about this? This will also have infinite solution, because the rank is 1 and the number of variables is 3. So infinite solution is there. I hope you have understood the topic. Now if you're new to my channel, please subscribe to my channel. It helps me to make more videos like this. And also don't forget to press the bell icon so that you can be notified every time when I upload a new video. That's it. Thanks for watching.